All right, so what we're going to be working on today is we're starting a whole new unit, and this unit's called exponential functions, okay? So something you guys need to know about exponential functions is the actual formula. So I'm going to zoom in a little bit. It's kind of hard to see, so we're going to write it down in our journal. Do you guys see where it says f of x equals a times b to the power of x? That's what I would like you guys to write down in your journal. So right here, we're going to title it, ready? Exponential functions. Okay. And I'm going to write down our formula, or not our formula, our equation, which is f of x, which is the same as y equals, okay? And we have a times b to the power of x. Now, what I'd like you guys to do is while we're doing this, all right, I want you guys to understand what a is, what does a represent, and what does b represent, okay? A will always be your initial value. So let's say we had, I don't know, a certain number of cases of, I don't know, coronavirus, okay? I'm not saying that we do, but let's say we did. All right, so let's say we had an initial value of, say, 10 cases. All right, so let's say our A value is equal to 10. So I'm going to put A equals 10. And then B, everybody, B I'll move it over here, represents what's called a growth, or it's referred to as a decay factor. Okay? A growth or a decay factor. So here's what you guys need to understand. If the B value is greater than the number 1, any number that's greater than 1, we consider it to be what's called a growth factor. Okay? But if B is less than the number 1, but it's still got to be what? Greater than 0, we call that a decay rate or a decay factor. All right? So let's say our B value was, let's say, let's just make it fun, like a 1.05, okay? 1.05. So let's say our function was f of x equals 10 times 1.05 to the power of x. All right? And so let's say f of x, in your journal right now, f of x equals the total cases. Okay, the total cases. And let's say x equals the number of days. Okay, the number of days. All right, let's just make a little table here. All right, so what do we initially start with? After 0 days, what's our initial amount? What should be the number? 10. So let's just figure out right now, after like a year, let's say 365 days. All right, if this was the growth rate, after 365 days, let's see what our y value will be. So let's go ahead and do a little Desmos here. All right, so I'm just going to type this in. Let's go to Desmos. And I'm even going to do f of x, okay? F of x equals 10 parentheses 1.05 to the power. So how do we do the power? The little right here, the power of x. All right, I'm going to zoom out. You guys see right here? Our point is at a what? 0, 10. So let me tell you something. This is kind of interesting. So in your journal, I want you guys to understand, whenever you guys have this, I want you guys to understand that in a table, in an x and a y table, at 0 will always be your a value. That's a very important information right here. In a table, whenever you plug in 0 for x, you will always start out with whatever your initial value is. Hopefully you can see I'm telling you the truth, because what was our initial value? 10. Look what happens if I change that to 100. Where is it? 100. So I'm moving it back to 10. Just showing you. Okay? Now, let's make a table. Okay? And we're going to type in 365. Holy cow. After 365 days, how many people were infected by the coronavirus? If this was, this is not true, guys. I'm saying we're just making this stuff up, so don't think we're saying it's true. So, holy cow, that's a lot, isn't it? So, what would that be like in real, like a real number without decimals? Ready? If I did 5.42, I'm just rounding it right there. Ready? Times 10 to the power of 8, what would I have to do? Take 5.42. You guys remember this? You got to move the decimal over how many times? 8, right? 1, 2, 3, 4, 5, 6, 7, 8. So we'd have what? 5, 4, 2, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, comma, comma. How many cases would we end up having? Whew, that's a lot of cases right there, right? So do you guys understand? All right? That's a lot of cases. Now, this is not the actual case, okay? But what I want you guys to understand when you guys are working on these problems, I need you guys to understand that this b value, now this b value is not even double, right? This is just 1.05. So what does 1.05 actually mean? If 1 is equal to 100%, what is 1.05 equal to as a percent? 105%. So basically, what is the growth rate here? The growth rate is growing at 5%. All right. So if something grows at 5% each day, if something continues to grow over and over and over and over again at 5%, that's where we get this 1.05. All right. So what do you guys need to know the difference between a growth rate and a decay rate? So what would be a decay rate? Let me show you what a decay factor would look like, okay? So let's say we had a whole bunch of stuff, like 10,000. Let's just do 1,000,000 cases, all right? There's 1,000,000 cases. And let's say the cases were actually decreasing, all right? So what would be a decimal that's less than 1 but greater than 0? Give me a decimal. 0.05, okay. Okay? All right? So, by the way, I can't zoom out that fast, but where would my y-intercept be? 1 million, all right? So if I put a 0, is that what? 0, 1 million. And so this is decreasing, all right? It's decreasing at 0.05. So it decreases pretty fast, right? Look what happens when I put a 95. I zoom out. Okay? So let's make it a more reasonable number, like say 10. All right. So I want you guys to see the difference between like it's reducing at 5% versus 95%. See how much that decreases a lot faster than that? This is decreasing at a 5%. And then the other one was decreasing at 95%. So you can see the difference. So what do we call this value? We call that the decay factor or the decay rate. Okay, so you're going to be learning more about that. All right, so let's go to our graph now. All right, these are some examples. So I'm going to go look at my graph here. So what I'd like you to do right now, okay, on your paper, what I'd like you to do is I'd like you to graph this to the best of your ability. Okay, so we're going to go over here. We're just going to graph it. We're going to do 2 to the power of x. Now, watch this. This is kind of cool. I want you to see the difference between 2 to the power of x and y equals 2 to the power of x minus 1. I want you to see the difference between, say, that number and that number right there. What do you guys see as happened in the graph? Watch this. 2, 4, 5, 6. You guys see how it shifts? So if I put plus 1, plus 2, plus 3, plus 4, do you guys see how things are shifted that way? So you can still learn how to shift things left and right in exponential functions. All right? So when you're typing it in, I think you have to use parentheses. I'm not sure. Yep, look. You actually have to use what's called a parentheses when you type it up there. All right? So here's what I want you to do. I'll go and clear this one out. There's our function. I want you guys to make a graph. There we go. Can you guys write down those numbers? Right there, just make that table right there, okay? As best as you can. All right, so right now what we're going to do is we're going to go ahead and plot these points right here, okay? So give me an ordered pair that worked. All right, so I'm going to put x, y, and I said go from what? Go from -1, right? -1, 0, 1, 2, 3, and 4. Okay, so -1 went with 0.25. What did 0 go with? 0.5. 1 went with 1. 2 went with 2, then 4, then 8. Okay, so here we go. So right now we have, you can see this is a 2 and a 2, so we'll put 2, 2 right there. Okay, 2, 2. 3 and a 4 kind of goes right about there. 4 and an 8 goes right there. And 1 and a 1 would kind of go right about here. 0 and a half right about there. So listen up. We're going to draw this as close as we can to being accurate. That was horrible. Man, I was so close. I was so close. There we go. All right. So right here, guys, let's write down the left-in behavior. You guys see where it says left-in behavior? Here's what I want you guys to do. Ready? As x, my bad. As x approaches -infinity, I want to know what f of x approaches. And as x approaches +infinity, I want to know what f of x approaches. So as x is going to the left, what does it look like my y value is getting really, 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 really close to, but not quite touching? 0, you're right. It's 0. It's not -infinity, because what? Do you guys understand right here? This is something you might want to put on your paper. This right here, that is what we call a horizontal asymptote. All right? So we have a horizontal asymptote, so you can label it on your paper, at y equals 0. Right there, that's our horizontal asymptote. But as x is approaching +infinity, where are my y values heading? +infinity. So this is the left-in behavior of this exponential function, and this is the right-in behavior of this exponential function. Okay? So right now, we're gonna look back at this. Okay, we're gonna look back at this, but I got to scroll down and we got to look at what the domain and the range and the intercepts and all that stuff are. Okay, so right now, let's take a look at the domain. If I go back, what x values are being plotted in this function? What do you guys think? What do you guys think? The domain goes from what to what? Yeah, goes from what? -infinity to +infinity. The range, though, the range does not go from -infinity to where does the range start? At a number slightly in front of what? Start, right? Is it equal to 0? No, so we have to put soft bracket 0, comma, infinity. Intercepts. What is the only intercept that it has? Does it have an x-intercept? No. Does it have a y-intercept? Could you guys see this table right here? Do you see that y-intercept? Where is our y-intercept located? So what I want you to do right here, it's got a y-intercept, put y-intercept at 0, comma, a half. That's the y-intercept. And there is no x-intercepts. You put no x-intercept. Asymptotes. Does it have an asymptote? Sorry, go ahead. Question. It has an asymptote. It has what? a horizontal asymptote. It's supposed to be not just, it's not ha. It's just a horizontal asymptote, okay? And where is our horizontal asymptote located? At y equals 0. And is this graph increasing or decreasing? It's increasing from left to right. So from left to right, we would say it's increasing. All right? And we're done. What I'd like you guys to do right now is I'd like you guys to do the exact same thing, except we are using what's called Euler's number. All right, Euler's number. Now, if you're wondering what Euler's number is, I think I gave you guys some notes on that. Let's see here. Oh, here we go. All right, so check this out. If we use this formula right here, if you want to read along with me, you can. Okay. So whenever you guys see E in the graphing calculator, check this out. If I hit, do you guys see the E right there? If I hit second E and I press enter, do you see that number 2.7182 and it keeps going on like that? That's called Euler's number. And if you look right here, it's calculated by doing this. So here's what I want you to understand. It's a limit. E is a limit, all right? If you use this formula right here. So let's go ahead and do it. Ready? Go to the calculator right now. Go to your calculator. Hit y equals. All right? I want you to open up parentheses, put 1 plus. I want you to do alpha y equals enter. And do 1 over x. And then I want you to raise that whole thing to the power of x. All right? Just like that. Now check this out. When I hit second table, you know what? Let's not, this is probably not good because this is fractions, so I need to change something. Let me explain something real quick. I need to delete this, and I actually need to do 1 divided by x this way. So we actually have decimals, not fractions, okay? There we go. Now we can see it. You're like, wait a second, that's not 2.718. But look what happens as I keep going. It's going to get closer and closer to that 2.718. Check this out. Second table. Watch what happens when I type in the number 1,000. What happens if I type in not 1,000 but 10,000? So as this number approaches what concept? As this number approaches what? Right there, as it approaches what? It's kind of hard to see. Zoom in. As that number approaches infinity, what do we get? We get this constant. This is an irrational number, okay? So you guys can read about, it's pronounced Euler, Leonhard Euler. All right, he computed it to 23 decimal places, but anytime you guys see E, I want you guys to understand this is the number we are talking about, okay? So in the calculator, do you guys see the word log and the word ln? This is logarithm, this is natural log. What do you see right above the ln? I don't know if you guys can see that. That's e to the power of x. So I want you guys to understand that whenever I say, what is e to the power of x, that's Euler's number. Okay? So if you're wondering how to get that in the calculator, that's what you would do. Okay, so let's go ahead and head back to our problem. This is a little table. This is just a little history you can read about, okay, on your own. So we are going to, I just want to make sure you guys knew where we got the E from. Okay, so let's go ahead and I'm going to zoom out just a little bit, and we are going to type that baby into Desmos. Go ahead and do it with me right now. All right, let's clear that out. We're going to type in h of x equals, and was it -1 divided by 5? Okay, -1 divided by 5. And I can just type in the letter E on Desmos because it knows that it's talking about Euler's number. And then what do we have? I'm going to take a screenshot real quick. E to the power of x minus 2. Okay. e to the power of x, and then we have what? Minus 2. Okay, look at that. Now, this is going to be kind of interesting. Check this out. That says what? Negative what? 2.2. Okay? So I'm curious right now if I would have typed in the same thing, not negative, that's minus. Negative 1 divided by 5. I'll help you out in just a second. E to the power of x, and then there's what? A minus 2, like that. Oh, you need to start at 0. There it is, negative 2.2. So what is this? That represents our what? Y. That's our y-intercept. Okay? So right now, what I'd like you guys to do is we're just going to do our best to sketch this to the best that we can. So right now, can you guys, right now, on your paper, that's negative 2. So right here, about negative 2.2, just put a point right there. All right? Now understand, do you see that minus 2? That minus 2, all right, is going to be really close. That's our horizontal asymptote. And if we go over here to our table, let's just find one number that we can kind of plot. See if there's a number we can kind of get. Oh, good. This is a good one. If I says 3, and that's what? Negative 6, basically. 3, negative 6. Just try to plot a 3, negative 6 as best as you can. So 3 would be right here. Negative 6 would be right about there. And just kind of plot that, go through that point, and that should be good enough. All right, so really, when you're graphing, obviously this graph is kind of hard to do by hand. What I want you guys to understand is at least understand that in a table, in an XY table, if you plug in a 0, you are going to be left with your A value. Now, here's the thing. What is our A value right now? If I said, what's our A value, what would you guys say our A value is? Negative 1 over 5. You're like, well, you're wrong. It's not negative 1 over 5. However, A is actually equal to negative 1 over 5, which is a negative what? 0.2. But what has happened to the graph? It's been shifted down 2 units. So if I take away 2 more, what does that give us? That gives us our negative 2.2. Does everyone understand how I got the negative 2.2? I could do that in my head if I make this what? If I make that a 0. Okay? Now, let's talk about our left-in behavior. You guys ready? As x approaches negative infinity, what does f of x approach? What would you guys say? As x is approaching as x is approaching negative infinity, what is f of x approaching? Nope. Nope. Negative 2, you're right. Negative 2. Because you guys see, we have a horizontal asymptote. See where it says asymptote? Put H, A. We have a horizontal asymptote at y equals negative 2. Why is it at a negative 2? Because the graph was shifted down 2 units. And that's why our horizontal asymptote has been shifted down 2 units. Okay? Now, this does not have an x-intercept, but it does have a what? It has a y-intercept at 0, negative 2.2. Over here, as x is approaching positive infinity, which means positive infinity is going to the right, what's happening to all of our y values? They're decreasing. They're going down. So where are they heading? That's right. They're heading to see Slayton. Going to go see negative infinity. Going down forever. All right. Let's just hope that pretty soon, like this will be your end result, all right, and not this. That would be bad. Okay. Now, what's our domain still? Our domain goes from what? Negative infinity to positive infinity. This is where our range gets kind of tricky. So where is it? Where is it going down from? Nope. going down from -2, so we're going to put soft bracket -2, and then it's going down to negative infinity. That's the range. So what I want you guys to understand is the reason we're doing this is because I need you guys to understand when I give you guys a quiz, I will be giving you an equation and asking you what the domain is, what the range is, what's the y-intercept, just basics about an exponential function, okay? So you need to know how to identify this stuff. Now, I will also ask you, is this graph increasing or decreasing? It's decreasing from left to right. Do you see how it's going down from left to right? It is totally decreasing. That's how we interpret it from left to right. Okay? Now, we are done with the two graphs. What we need to do now is we need to look at the word problem, and we are now going to start using our calculators to help us solve these word problems. Okay? So we're going to start with number 3. Okay? It says, in 2000, the number of people in the United States was 281,421,906. The U.S. population is estimated not to be decreasing, but growing at 0.88% annually. Let t represent the number of years since 2000. Write a function that models the annual growth in the population in the U.S. So listen up. Here's what I need you guys to understand about percentages. So can you guys, in your journal, just talk about percentages? So write these things down, okay? Just remember, 100% as a decimal is 1.00. 90% as a decimal is 0.90. 5% as a decimal is 0.05. 0.5% as a decimal would be 0.005. So what I want you guys to understand, if you ever have a percentage, all you have to do is take that percentage and divide it by the number 100, and that will give you the decimal equivalent. This is pretty important that you need to understand how to convert a percentage to a decimal. So what is our decimal, everybody? It's point what? 88%. So if I took 0.88 and I divided that by 100, what would be my decimal equivalent? Point what? 0088. Can you guys see that? 0.0088. This is what we have to use. Because if it's estimated to be growing at that percentage rate annually, that's going to impact our formula. So here's A. Okay? And I'm going to put f of t. Now, f of t will be the total population. And what was our initial? What's our A value and what's our B value going to be? And t represents time. So we have A times B to the power of t. That's supposed to be an A. Try it again. A times B to the power of t. I'm going to pause the video, see if you guys can figure out what formula using this percentage. You got to find what's called B, which this place is going to be a growth rate. Okay? See what you guys come up with. All right, so we have f of t. It's supposed to be a t. It's not a very good t. What was our initial population? 281,421,906. That's our A value. Now, this is the part where students need to understand, like, what do I do to build that? Would you guys agree that this population in the year 2000, that was 100% of the population? And what percentage are we adding to it? We're adding point what? 88% annually. Would you guys agree that would totally equal 100.88%? But how do I write that as a decimal? What would I have to divide everything by? 100. So what does that become when we do this divided by 100? It becomes 1.0088. That's the growth. That's the growth rate right there. And then we raise it to the power of t. And this is our answer. well, okay, listen, T represents years. Okay, T represents years. All right, now, T represents the years since 2000. Okay, the years since. So it says predict the population in 2020. So then what would I do? I would plug in a 20, and then I would plug in a 30. So we're going to go ahead and make that. We're going to make that prediction. So right now, could you guys just go to your calculator real quick? So go to your calculator. Okay, hit y equals, and we're going to type in, what was the population again? What? 281. Okay. 281,421,906. 906. Parentheses 1.00. Is it 0088? Make sure. Yep. And I close that. I got to raise that to the power. In this calculator, I'm going to put power of x. Now here's what I'm going to do. I'm going to hit second window, and I'm going to start the table at 20 because that would be in 2020. Wow, that's kind of weird. Hey, how about this? You guys see that right there? What are we at now? What does that represent? 335 million. 335 million. Okay? And at you guys see the 30? I'm going to highlight the two answers. You guys ready? Here's one of our answers right here. Here's our other answer right there. So, in 2020, which is this year, what are we going to write? 335 what? Million. And over here, we're going to write 366 million. I'm just curious. Yeah, yeah. All right. Current population of the U.S. Wow. Hey, by the way, do you guys see right here? I'm not moving the dot, but do you guys see the population of the United States? 2000. What does it say? 282.2. Correct. All right. And what did we use? See where it says 281 right there? That's kind of cool. Pretty accurate. Pretty accurate. Not bad. Okay. All right. All right, guys. Here we go. Last problem today. It says determine the amount of money in a savings account that provides an annual rate of 4% compounded monthly if the initial deposit is 1,000 and the money left in the account is 5 years. So guys, here's what I want you guys to do. Can you guys look for a formula on your paper that I gave you? Here's the formula you need to look for. Ready? A equals P parentheses 1 plus R, it's supposed to be an R divided by N to the power of NT. Now, guys, I want you guys to understand what each of these letters mean, okay? So can you please write this down? All right. Everybody, P represents the principal, not principal LE, but principal, okay, which represents the initial amount. So the principal represents the initial amount of whatever you have put in, okay? R represents the rate as a percentage, okay? N represents the number of times it's compounded. Number of times it's compounded. And A represents like the final amount, okay? Like what the final amount would be, okay? So if we were going to use this formula, and by the way, this formula is one of your formulas that I've given you. It's the compound interest formula, okay? So check this out. What's our initial amount? 1,000, okay? Parentheses, 1 plus. What's the annual rate? 4%. So how do we write that as a decimal? 0.04. It's compounded what? Monthly. If it's compounded monthly, what would our N value be? 12. We close it and we raise it to 12, which is still the end value. And what is t? Oh, I forgot to put t. T equals years. Okay? All right, so t equals what? 5. There we go. That's how you set it up. No. Well, 12 times 5 is 60. All right? So here we go. Go to your calculator. This is the last thing we're going to do today. All right? Check it out. Let's go to our calculator. We're starting with what? 1,000. With $1,000. We're doing 1 plus 0.04. What are we dividing that by? 12. Close it. Raise it to the power of what's 5 times 12? 60. And in 5 years, how much money will you have? Not that much. Now listen up. Let me tell you something. Watch what happens when you change the percentage. You guys ready? Percentage matters, guys. This is at 4%. What if you earned 10%? Now, how about this? Last thing. What if you started with $10,000? No, it's not. I inserted it. $10,000, you left it for 5 years. Okay? So we're going to talk about more about compound interest tomorrow, all right? And how it will work for you if you wait long enough. Y'all have a good day.